Okay, thanks for coming, everyone. I'm going to be talking about an introduction to nilsystems. So today's talk, I'm just going to give sort of some context to be thinking about nilsystems, where they come from, and how they sort of extend some ideas that are easier to get a handle on. So I think, at least probably for most of you, there's not going to be a whole lot new today, but just to sort of review some concepts about nilsystems. Maybe you haven't seen all of these pieces, but just so we have a solid foundation. And then next time, I'm going to focus on discussing some results about equidistribution in nilmanifolds, and discuss maybe some more extensions of these ideas and what happens for things as like if you want to look for polynomial progressions or more general kinds of sequences. But today it's just going to be talking about how nilsystems arise for controlling linear averages and understanding arithmetic progressions. Okay, so let me start by just introducing multicorrelation sequences. So our setting for all of this today, we have some probability space and a measure preserving transformation. And maybe I should add a word here just so I don't have to worry about it. Let me make it invertible. And something we might want to understand, this is a very broad question, but given some measurable set with positive measure, what can we say about these multicorrelation sequences where we take A intersected with t to the minus na all the way up to t to the minus kna? So this sequence is encoding some information about arithmetic progressions. And if we want to study things like Szemerédi's theorem or refinements of it, we want to understand these sequences. And I've written a more general sort of form of these sequences below. We could also, instead of just looking at some set A, it's often helpful to make this into a multilinear expression. So we take k different functions and then understand how these sequences behave. Right, and so one thing, I guess, one version of Szemerédi's theorem would be that A of n is positive for some non-zero. So this is in this first situation. And of course, we can say more than that. We can maybe say something about the largeness of the set of n's that give you positivity. We can maybe get better bounds than just being A of n being positive. But these are natural things to study for some combinatorial applications. And the simplest case is if we just want to look at single recurrence. And so I'm just going to review some things about positive definite functions. So we say a function or a sequence is positive definite if we have this expression here, which I think hopefully you've seen before. I don't want to try explaining it too much. It's related to positive definiteness of certain matrices that you could form out of your sequence. But the thing to have in mind is maybe just these examples here. So some sequences that are positive definite are these correlation sequences, the measure of A intersected with t to the minus na. And another natural class of examples is the Fourier transform of some positive measure on the circle. And maybe I should have the word finite here. Let me just throw that in. And you can check. So maybe the first one is the easiest one to check positive definiteness, you can write it as an inner product. And then when you try checking this condition, you use linearity a bunch of places and end up with some quantity squared, so it has to be positive. And why does this help to know that this correlation sequence is positive? Well, we have Ergodic theorem, which says that actually every positive definite sequence is just the Fourier transform of some measure. And this is extremely useful. I use it all the time for trying to do things in ergodic theory. But it's not so surprising. So if you want to, I'm not going to prove it, but the sketch of the proof, what is a measure? It's a linear functional on continuous functions. If we're given our positive definite function, that's telling us how we should integrate all of these functions, e to the 2 pi I n x. And if you start taking linear combinations of those functions, you're going to get uniform density in the set of continuous functions. And so you can just define your measure by taking some linear combinations. The key sort of technical detail that I'm leaving out there, of course, is this needs to be well defined, and that's where the positive definiteness of the sequence is going to come into play. Also to show that this thing that you define is actually a positive measure and not some complex measure. Okay. And this tells us some nice decomposition for a single correlation sequence. So if we just look at the measure of A intersected with T to the minus NA, we can write it as the sum of two pieces, which I want to think about as sort of a structured part and a random part. And the structured part has the structure of an almost periodic sequence. And because I want to do dynamics, I've represented it in this dynamical way as a continuous function evaluated along an orbit in a compact group rotation. And the second piece is a null sequence where we get some limit going to 0 in density. Okay, and what's the proof? I'll just sketch it out. We use Ergodic.
I have a question about the null sequence. So is it going to 0 along all Fulner sequences or just along some Fulner sequence?
All.
Okay.
So yeah, so this is as, say, n minus m goes to infinity.
Okay, thank you.
Yeah, so this is like the compact weak mixing decomposition, and things are happening. So I'll write up some sketch of details, but the kinds of limits we're dealing with are more like L2 limits than pointwise limits, and we'll be able to deal with doing things over any Fulner sequence whatsoever in all these situations. So, right, so the proof of this is we write we know we can write this as the Fourier transform of some measure, and then we just decompose the measure into the atomic part, and the continuous part. And that's basically the end of the proof. So the atomic part, you're just looking at a bunch of atoms. So you're looking at sums of like specific trigonometric functions. And so you'll get something almost periodic. The continuous part, statement 2 here is just applying Wiener's lemma to the Fourier transform of the continuous part. So not a very complete proof, but that's how this works out. Okay, and this is very useful to have this decomposition. We know, right, compact group rotations are much easier to understand than some general measure preserving transformation. And if we're looking at single correlations, all we really need to understand are compact group rotations. Okay, so this is sort of the beginning of the picture for multi-correlation sequences. If we're studying something, for other versions of extensions of Szemerédi's theorem, we might want to look at multiple ergodic averages instead. And so these are, related to multi-correlation sequences. But here we're looking at some limits now and not taking integrals. So these are other natural things to study if you want to understand arithmetic progressions or more general combinatorial configurations. So we want to understand the limiting behavior of this product of functions, and I'm missing an n, I think. Okay. And, well, at least a sort of standard approach, a very useful approach for understanding these averages is to understand characteristic factors, which I'll talk about more what those are in a bit. But instead of looking at our functions, fi's, we can simplify. So looking at the projection onto some subspace. And hopefully we can get some structure on that subspace that makes these averages easier to understand.
So it should be t to the in on both instances on that line, right?
Yes, it should. Okay. And so I switched some notation here so I don't have to keep writing this big limit with Gizarro averages. So UC_lim means uniform Gizarro limit and is the same thing. So this means this thing, just in case that's not clear. Okay, and I guess I didn't really say where I'm studying these averages. Again, for everything I talk about, I'm going to be taking these averages, say in L2. All of the functions are going to be L infinity functions so that we can multiply them and they stay in L2. And when I'm dealing with L2, I can take really these uniform Gizarro limits. I don't need to restrict my Fulner sequences. Okay, and the simplest example of understanding some projection is the mean ergodic theorem. If we take the uniform Gizarro limit of t to the n applied to our function f, this is going to produce an invariant function, a t invariant function, and it's just the projection onto the invariant sigma algebra. Right, so this is classical, it's just the invariant ergodic decomposition of L2. And, the ergodic theorem is useful all over the place. So maybe, right, and then this, of course, if it's ergodic, this is just the integral of f. So the first, sort of non-trivial results in this direction is if we look at t to the n f1 and t to the 2n times f2. And here, the averages are controlled by the Kronecker factor. And this is another appearance of rotations on compact groups. So just like if we wanted to understand how mu of a intersect t to the minus na behaves, it was enough to understand compact groups. if we want to look at multiple ergodic averages of this form, we basically just have to understand actions on compact groups. And this, if you want to prove this, the key tool is the van der Korpit trick. So if you use van der Korpit and you know the ergodic theorem, you can prove this result without too much having to happen. One thing I should say here is this is assuming T is ergodic. Okay, and again, having this sort of structural information is really useful if we want to do applications. So for studying Roth's theorem, that would be proving the positivity, say, of this limit on the left. And by knowing that this is controlled by the Kronecker factor, we can actually write out a fairly explicit formula for this limit. So, you can prove Roth's theorem by using the compact weak mixing decomposition of L2, applying some van der Korpit tricks, and just getting positivity. With this is actually not so different. We're still basically using the same splitting and applying some van der Korpit. We can get some more information and actually compute this limit of the triple correlations. And if you do just a little bit extra work, you can prove this strengthening of Roth's theorem, where we actually get return times where the intersection is large. Okay, so this is sort of the background picture, what happens up to the level of the Kronecker factor or compact group rotations. And already we've seen some useful results as consequences of this. So then I want to move into what happens for longer expressions. But are there any questions so far?
So the Kronecker factor to me is kind of this mythical thing, I suppose, because I hear it referred to all the time, but I have not once read about a description of it ever.
So
so I guess my question, my main question is like, what is the reference for Kronecker factor? Like what, where is it described fully in a book?
Okay, under just put in, and so their word, I guess, has a good description.
Okay. Now, is it referred to as a Kronecker factor in that book? Like, do they use that same terminology? And see, learn word. Okay, cool. All right, thank you.
Yeah, I mean, I can say some very quick things, maybe. Oh, well, Michael's left. Okay.
I now have my book.
Yeah, so it's maybe useful. I can say some quick things because this will be helpful for what I go into next. So the Kronecker factor, we can think of, it's describing the compact portion when you do the compact weak mixing splitting.
Right.
And so we can look at one way of defining a factor is actually just to take some T invariant algebra of functions. And so your algebra of functions here is just, so you have algebra of functions given by linear combinations. of eigenvalues, eigenfunctions. So we have some eigenfunctions in the system. Just take all their linear combinations. This is going to give you an algebra, because if you have, say, two eigenfunctions with values lambda and mu, T acts in a way that respects products, and so you'll end up with lambda mu times your original function. And so if you multiply eigenfunctions, you get back an eigenfunction, and then we just take all the linear combinations. This gives you an algebra, and the Kronecker factor is just the sigma algebra generated by all of those eigenfunctions. So when we take conditional expectation, we're just, looking at the compact part in the compact mixing decomposition.
Okay. You mean you said the sigma algebra generated by the functions? Oh, you mean the sigma algebra, like the smallest sigma algebra such that all of the eigenfunctions are measurable.
Right.
Okay.
Yeah. And it turns out that you can describe this. So I'm claiming this is a rotation on a compact group. The way you can get that is if you take all of your, so maybe I'll take lambda to be the set of eigenfunctions. So there exists f with tf equal to lambda f. This is going to give you a group. And if you take you treat it as a discrete group and then take its dual, this is actually going to give you the action on the compact group. So T then acts on, how does it act? So T, Z at lambda is lambda times Z of lambda. I think this is right. I may be cheating slightly. But the point is this compact group comes from just looking at your eigenvalues. You can take the dual, and there's some simple construction to actually view what's happening on the Kronecker factor as a group rotation.
Okay, thank you.
So I think that's enough detail to make sense of what's going to happen next. But I at least wanted to make it clear that this is eigenfunctions controlling this, which is some sort of linear behavior in the system, because if we start taking T to the n, we're going to get lambda to the n. We have some sort of homomorphisms underlying this. So we just want to think about this as sort of linear behavior. And now I want to think about, if we look at trying to study some longer progressions, what kinds of behavior are going to have an impact on the structure of 4-term arithmetic regressions. So in some way, what we saw on the last slide was that for 3-term arithmetic regressions, this is controlled just by sort of linear behavior. And for 4-term progressions, we're going to see some quadratic behavior and maybe a bit more. So I've written down an example system here, which is the sort of basic skew products that you've probably seen 100 times. We take x plus alpha, y plus x. And if we start taking orbits of points here, we're going to get some polynomial behavior. So we get x plus n alpha, y plus nx plus n choose 2 alpha. So we have some quadratic things appearing in the second coordinate. Now, if we started to look for 4-term arithmetic regressions, this quadratic behavior is going to restrict how things behave, because anytime you have a quadratic function defined at 3 points, you've fully defined your quadratic function. So in particular, there's this relation, which I've hopefully written down correctly. If you take your point plus 3 times its orbit under, or its image under t to the 2n, that's the same as t to the 3n of your point plus 3 times t to the n. So I think I put the 3's in the right places and things on appropriate sides. If not, at least some relation like this holds. And so once we know where our point is, where it is under t to the n and under t to the 2n, t to the 3n can only be one place. So this quadratic behavior is going to influence how 4-term arithmetic progressions can be appearing. And you might suspect, well, in the 3-term case, we only need to worry about linear things. Does that still happen? And the answer is no. So there's a little bit more general of a setup where we can have these restrictions on what's happening with 4-term progressions. So I've written out an explicit example. This orbit, so this particular system, I took from a paper of Bergelsen and Leibman on generalized polynomials. But there are other systems you could write down like this. So we take the Heisenberg group. Hopefully it's clear what I have indicated here. We have ones along the diagonal, and then in the upper right, we can put in any real numbers, and we quotient out by that group where we put in integer values. And then I'm going to take a specific group element with a minus alpha, a beta, and an alpha beta in convenient places. And if we look at how this group element acts on the quotient space, we can write this out and get this particular orbit. So there's some manipulations that I skipped here. If you just take the nth power of g, it's not going to look like this, but because we have modded out by gamma, you can do a bunch of manipulations and bring all of the those 4 coordinates back into the 0, 1 interval. And when you do that, we get some interesting behavior in this coordinate. So this is some kind of generalized polynomial. It's almost quadratic, but it's not just a quadratic function. And you're not going to be able to get this sort of behavior from such a simple algebraic skew product as the previous example. Okay, but why do we care about this? Well, we still have, so this is not a quadratic orbit, as I said, but we still have some identity on the level of the group G that looks similar to what we had before. So if we take some products and convenient powers in the group G, we'll get the identity. And so again, if we have 3 of these determined, if we know 3 of these, the 4th one is fully determined. And so this is going to be influencing the behavior of 4-term progressions. And I'm hoping I've written down a correct identity. I didn't actually check this, but I think this is supposed to be true for any 2-step nilpotent group. Something like this holds. That I can believe. I can say confidently. Okay, right. So the point is we get some correlations in this orbit that's controlling 4-term progressions. Okay, so if we want to understand longer progressions, it's not enough maybe to just look at these simple skew products with the torus. We might also need to look at this group. Maybe we'd have to look more generally. we can at least try to describe a class of systems related to this second example. And this is exactly the class of nilsystems that now I will finally define. So now it's going to be some abstraction. You should really just think in your head, G is like this upper triangular real matrices, and gamma is like upper triangular integer matrices. That should give you a good picture of what to think about. But in general, we can take some k-step nilpotent group, and then we mod out by a co-compact discrete subgroup. And the point of making it co-compact is so that we actually have a nice probability measure sitting in our quotient space. And this quotient space is what we call a nilmanifold, in this case, a k-step nilmanifold, referring to the sort of complexity of the group we started with. And this nilmanifold supports a Haar probability measure, which will denote mu sub x or mu sub g mod gamma. Maybe I should say, so what do I mean by Haar probability measure? X is not a group. What I mean is mu x is G invariant. So G acts naturally on this quotient space, and there's a unique measure that is invariant under all of that action. Okay, so a nil system,
I guess in this case, it's only the left action.
Yes. So I'm taking the left action because I'm modding out on the right.
Okay.
Yeah, so there's not even a natural way for G to act on the right in this situation. Okay. And so this is some, more general thing than what we looked at before. So if we look at, I didn't write this down, for one-step nilpotent groups, that just means you're an abelian group. And so we'd be looking here at a compact abelian group, would be a one-step nil manifold. So our Kronecker systems are one-step nil systems where we had a specific rotation. Our k-step nil systems are now we multiply by some group element on a nil manifold. And so this system is a nil system. You might call this action T. Maybe a nil translation. And then we'll also want some notions of nilsequences, which are formed from nil systems the same way we got almost periodic functions from group rotations. So we take some continuous function and just evaluate along an orbit for some nil system. So now I lied a little bit. That's only a basic nil sequence, a k-step nil sequence. We need to be able to take uniform limits. So in the case of compact abelian groups, if you take a uniform limit of almost periodic functions, you're going to get, again, an almost periodic function that you can describe by a new compact abelian group. In this case, you're not going to be able to do that. And maybe let me add a word here that makes that make more sense.
Okay.
So if I add the word lead group here, which I should have had from the beginning, not every compact abelian group is a lead group. And if you want to get all almost periodic sequences, you have to take uniform limits of ones coming from compact lead groups. So the same sort of thing happens on the level of abelian groups. It's just that there's no real reason to care so much about Lie structure when you're dealing with a simple object like a compact abelian.
So yeah, I had basically a question, which was all of the terminology here makes sense to me, except for why are we calling it a nil manifold? But now that it's a Lie group, I'm good.
Yes, it does have manifold structure. Okay, so before we had this decomposition for single recurrence in terms of a rotation on a compact group and something negligible, this null sequence. The amazing thing is if we want to look at multi-correlation sequences, we can get a similar decomposition. And so this is the Bergelsen-Host-Krah decomposition of multi-correlation sequences. If we take any multi-correlation sequence, we can decompose it as a sum of a nil sequence and a null sequence. And one of the applications of this, really the main application in the paper where they prove this decomposition, is a strengthening of Szemerédi for 4-term progressions that we can get large intersections for length 4 progressions. And the way they do this is by using this decomposition. The null sequence doesn't really affect this set, at least synthetic behavior of sets. And then you can get your hands on this by understanding how nil sequences behave.
So does this theorem, the second theorem, does this apply to that skew product that you gave at the beginning? Because you said that having 4-term arithmetic progressions is difficult, but still you have synthetically many.
So what happens with that skew product? So if you have, okay, what's the easiest case for proving this theorem? Take a weakly mixing system, and then the limit of the measures of these sets is going to be exactly mu a to the 4th. And so immediately we get that this set is synthetic. What happens for one of these skew product systems, at least if you choose your A in a way that really sees that sort of quadratic behavior, is you'll actually get, so the limit might be quite small, but you'll get that A sort of behaves like a 4-term progression. And so there won't be very many values of n for which you're going to hit a progression. But for some values of n, you'll get very close to mu of A, actually, as your intersection. So I might be cheating a little bit. This is easier on the level of looking at things in like Z mod and Z and doing similar analysis there. But basically, if you have this, so outside of your behavior coming from your nil system, it's going to the correct limit. And then on the nil system, you're maybe getting some very structured pieces so that you're not going to the correct limit, but you're still going to get positivity for reasons of maybe like topological recurrence.
Okay.
So that was very hand wavy, but hopefully gives some answer. Okay, so this is very nice. This is extremely useful for understanding multi-correlation sequences. And next time I might talk about some things for multi-correlation sequences for more general progressions. like polynomials or things coming from party field, the kinds of patterns that people studied. You could look along primes or shifts of primes, all these kinds of things, and having this nil structure is really helpful. So let me go back now to thinking about characteristic factors. And before I talk about them more, I just want to make sure, now I'm really going to make sure that I'm explaining what a factor is. So if I'm thinking about a system as a factor of another system, that means essentially that I have this commutative diagram. There's some technical details here. I need to throw out maybe measure zero sets because we're dealing with things measurably. Measure zero sets don't really matter, but essentially you have a projection down to your factor, and the factor, the map commutes with that projection. And we can also then lift the sigma algebra from Y back into X. So I could look at the inverse image of the sigma algebra inside of the sigma algebra B, and this will be some T invariant sub sigma algebra. The T invariance comes because we have this commutativity of the diagram, and we'll also, maybe think about this sub sigma algebra as a factor, so that we can really take projections in a reasonable way, like taking conditional expectations. Okay, and so, right, nice example. Look at that skew product we saw before, and we can take just the first coordinate. That's also a measure preserving system, and we can view the x plus alpha as a factor of the skew product system. And we really have this sort of, I've drawn this picture to try to see this product structure of the map T. We have S on the base, and then we have something happening above. We could just project everything down to the base and be looking at that. And in this situation, S is the chronic factor of this system. Okay, so now I'm going to give a definition that's not super precise. But I want to say that a factor is characteristic if it controls some multiple ergodic averages. So if we can replace our function by its projection onto this factor. And to say that it's characteristic, I need to specify what sequences I'm looking at. So maybe I should say it's characteristic for the family of sequences A1 through AK. And if we're looking at linear patterns, I'm going to give these a specific name. I'll denote by ZK minus 1. So there are some factors that control length K linear averages that we denote by ZK minus 1. And now I want to give some indication of how to understand these factors and what structure they have.
Characteristic, does this mean for any sequence, sequences AI of n, you will have this, or is it characteristic?
So this is my being sloppy. So for
okay, thank you.
So you say,
and again, this is happening maybe in L2.
So you say the characteristic factor. So is there sort of a general way of constructing this z sub k minus 1?
Yeah, so I'll get to that. So yeah, so I should say, right, if you have, so X, you have your system X, whatever patterns you throw out there, X will be a characteristic factor, right? If I take the projection onto X, I'm not doing anything, and so I'll get this identity. So to make things useful, you probably want to take the smallest factor that controls the averages. So you're right that the characteristic factor is maybe bad terminology, but if you take the smallest one, then that would be
Okay.
fine.
Well,
And depending on the situation, sometimes you don't. Sometimes, in some situations, it's okay to work with one that's not minimal, but maybe at least isn't too much bigger than the minimal one.
So I guess what's not clear to me is how are, because I mean, when you take the smallest, there's some way that factors are contained in one another, but that's not clear to me how you would define containment of factors, just that
Inclusion of sigma algebras, right? So if you think of your factors as sub-sigma algebras, you can take an intersection of all of these sigma algebras, and that will give you a smallest sigma algebra.
Okay.
So yeah, with systems, it's maybe hard to see how things work, but if you go back to sigma algebras of the original system, there really is a minimality.
Okay.
Okay. So one approach that's very convenient for understanding these factors is this family of seminorms that was first introduced by Gowers in the finite setting. So Gowers had a proof of Szemerédi's theorem doing everything in the integers mod n. And the way he did this was introducing a bunch of seminorms that were then sort of transferred into the ergodic setting by Host and Craw, and led to an understanding of these characteristic factors. So to define these, we need some more notions, and the notion of a relatively independent joining of a system with itself with respect to its invariant sigma algebra. So we could define relative independent joinings more general situations, but we don't need to here. So this is a measure such that when you integrate some function with this nice form over here, it's sort of a product of functions in the different variables, this becomes the product of their conditional expectations on just the system X. So these are now evaluated, say, at X and X, dv of X.
Ethan, here you are assuming ergodicity for T.
Yeah. I maybe should have assumed that a while ago. Always assume my system is ergodic.
Yeah, after you said the Furstenberg Weiss result, I guess that you were using ergodicity. Okay.
Yeah. Yeah, I just didn't want to write my assumptions everywhere, but that is a good point. I do need to be dealing with some ergodicity here. So, okay, so for this system, well, okay, so if my base system here is ergodic, then the invariant sigma algebra is trivial, and my relatively independent joining is just the product. Because I'm joining, it's relatively independent, so the only sort of dependence is happening in the invariant sigma algebra, but there's nothing there. So here we're going to get a product measure, but then we can define this inductively. So the first stage, we're just taking this over the invariant sigma algebra in T, and then we're going to keep doing this construction with a relatively independent joining, but at each stage now we're looking not at the invariant sigma algebra for t, but this big product of t 2 to the k times. And so you can maybe believe that this is going to be telling you something about the structure of, you start with invariant things, and then you're getting more and more structure of things that are not invariant, but somewhere sort of low down in complexity, where if we had some weak mixing system, all of these t to the k's would be ergodic, and we'd be getting totally uninteresting measures. So for weak mixing, we're expecting things to really just separate into products, and it's some sort of non-weak mixing behavior that's going to be slowly detected as we go up in levels with these measures. And then we can define some seminorms from these measures. This expression, sorry, is kind of ugly because I want to represent it in some reasonably compact way. We just take a function, take a tensor product with itself, and if, so we're indexing these by 0, 1 sequences. If there's an even number of ones, we'll just take the function itself. If there's an odd number of ones, we're going to conjugate it. And this is for reasons of basically positivity. We need to throw in some conjugation to make things positive. And this will define a family of seminorms. So let me just look at the simplest example to get some sense out of this. So when k is 1, this expression is we take f tensor product with its conjugate and integrate with respect to mu1. And mu1 was defined as the relatively independent joining with respect to the invariant sigma algebra. So we can replace this integral by an integral over x of some conditional expectations. And now we just have a function and its conjugate. So this is the L2 norm of the conditional expectation. We want to deal with ergodic systems. And so this is just going to give us the integral of f squared. So we'll have one seminorm equal to 0 whenever f is in the ergodic component of the L2 space. And it will be non-zero if it's in the invariant piece. So maybe I should have gone to the next seminorm, but if you go to the next seminorm, this is going to be looking at the invariant sigma algebra for t cross t, which is closely related to the Kronecker factor. And so the second seminorm is detecting this Kronecker factor behavior, or these sort of linear correlations. And the key properties that we might care about, there may be some others. These are seminorms. As I've sort of suggested by thinking about these as levels of complexity, the seminorms are non-decreasing. So, right, as I said, anything that's in the ergodic component is going to have one seminorm equal to 0. But if it's sitting in the Kronecker factor, then we'll have some t cross t invariance happening. And so it's 2 seminorm will all of a sudden be positive, and then all of the higher seminorms will as well. And if we look at some collection of functions and take these sort of cubic configurations, we can bound that by a product of k seminorms. So if we look at basically the multilinear version of the expressions defining the seminorms, we can bound it by the product of the seminorms. And what Host and Crowd do is show that these sort of cubic configurations also govern the arithmetic progressions, the linear structure for recurrence, and you can define these factors zk in terms of the seminorms. So the seminorm is equal to 0 if and only if its projection onto the k-1 factor is 0. So we saw this in this sort of trivial case where k is 1. Z0 is the invariant sigma algebra, and this works out fairly easily, but this continues on and gives a way of understanding these factors. Okay, and the last result that I'll end with for today is that ZK actually has nilpotent structure. So it's something that's not terrible to show. There's still plenty of work that goes into this, but because of the relative independent joining sort of structure that we had on the seminorms, you can show that the ZK factor is a skew product extension of the k-1 factor. And then with additional effort, that takes maybe a lot of additional effort, you can get from this some nilpotent structure. And the theorem from Host and Kra, I'm also writing Ziegler here. Ziegler has a different approach to producing these factors, but proves essentially the same thing. This factor zk is an inverse limit of k-step nilsystems. So if we want to understand progressions of some length, we just need to understand sort of the structure of nilsystems for that complexity. And so this gives a sort of structure for what a measure preserving system looks like. So in Furstenberg's original proof of Szemerédi's theorem, he shows that you can construct any system by starting from the trivial system, doing a bunch of compact extensions, and then at the end you throw on a weakly mixing extension, and that gives you your whole system. What this theorem tells you is something more precise about this. So we have this sequence of factors zk that are controlling progressions of specific lengths. And they're built by compact extensions. Way out on top of all of these is the distal factor, which is sort of the top of this tower of compact extensions. And then from the distal factor to the system itself, you just take one more extension that's relatively weakly mixing. And depending on what kinds of patterns you're looking for, you'll be caring about some different level in this tower. And so next time I'm going to talk about how we actually use this structure to, I mean, this seems helpful. We have some very specific structure that we have on each of these factors. So I'll talk about some results for nilsystems that we can then apply to understanding all kinds of combinatorial configurations for the integers.
Very nice, thank you, Ethan.
Okay, thank you for the talk.
Yeah.
Can you scroll back to the page with the formula of the Gowers host cross seminorms?
Yes.
I just wanted to see that again. I don't have a specific question about it, so other people can ask if they do. But
Is this a good portion of the page?
Thank you.
So I didn't write it here. You can also get these seminorms through, you can, instead of doing the relatively independent joinings, you can look at some, like go directly to defining the norms in a recursive way by taking
Van der Korpet-like
nicely chosen Van der Korpet sort of expressions. Yeah. So this condition, this relative independent joining is really encoding a van der Korpit, like one application of van der Korpit, but you can define the norms directly in this van der Korpit way, which is at least makes more sense in the finite setting as well, because doing like conditional product things is strange, but this is a little bit, well, I wrote it down this way, but you can do it that way as well, and maybe see why progressions are appearing here.
I mean, you can still kind of see the van der Korpit here with that C to the sum of the epsilon I map. That reminds me of the van der Korpit a little bit.
Right, because I guess it's counting how many times you've like taken differences, and each time you take a difference, you get one conjugation.
Yeah.
Can you send us, Ethan, the notes as well?
What was that?
Can you send us the notes?
Yeah, sure. I can just share this file.
Thank you. I would also put the property of the product of F with its conjugate, the K Seminor, that it's bounded by the square of the K plus 1 Seminorm of F. This is something that we also use all the time. And it's not trivial to show.
So what was that?
In the three properties that you are listing, I said that I would also add the property of the product of F with its conjugate.
Right.
And actually, I was just thinking, if you can go back to the formula again, what is the argument of F in the integral? Because F was defined on the original space X, right? But you're taking an integral over X to the 2 to the K. And I can see the measure mu is defined on that space, but
So let me write out this. So what does this tensor product thing mean? It means I'm doing like F of X1. Okay, so actually it's going to be easier if I index my variables by maybe binary sequences. So we do F of X, all these zeros, F bar of X at this binary sequence, and then, F bar X, a bunch of zeros, a 1, 0.
Okay, that actually makes a lot of sense. I feel a little embarrassed that I didn't interpret that part, but
so yeah, so they're all defined on different variables that I'm indexing by binary sequences, and I conjugate if there are an odd number of ones in the binary sequence.
Okay.
So we'll see each other next week, I guess.
Yeah.
Thank you
I guess
again.
we can also end the recording, see if there's any off recording questions before we decide to disperse.